Before we begin tonight, I want to tell you about rain. Not the rain outside your window, not the familiar sound of water on glass, a different kind. On a planet called WASP 76b, about 640 light years from Earth, it rains iron, liquid iron, falling from the sky like raindrops, but made of metal. The day side of this planet faces its star permanently because it is tidally locked. One face always toward the star, one face always away. The day side temperature reaches approximately 2,400 degrees Celsius, hot enough to vaporize iron to turn solid metal into gas. The iron vapor rise in the intense heat moves around to the cooler night side, where the temperature drops enough for the iron to condense back into liquid droplets and fall as iron rain from an iron cloud on a world 640 light years away. This is real. This has been measured, confirmed, published in a scientific journal. In 2020, a planet where it rains iron. Tonight, we are going to visit the strangest worlds the universe has produced. Before we do, tell me where in the world you are right now. What country, what city, what time? Drop it in the comments. I love knowing where people are when they listen to these. Now, let's go exploring. Opening cinematic. The universe is not what we expected when astronomers first began to think seriously about planets around other stars. In the 1980s and early 1990s, they expected something like our solar system, small rocky planets close to the star, large gazon. Further out, an orderly arrangement shaped by the same physics that shaped our own neighborhood. They were wrong, so wrong that the first confirmed exoplanets, actual planets orbiting other stars, were so strange that astronomers thought the detections must be errors. Pulsar planets, worlds orbiting a dead neutron star where no planet should survive. The sheer strangeness of the discovery made many people doubt it. Then gas giants, the size of Jupiter or larger, orbiting their stars in days at distances smaller than the orbit of Mercury around our Sunday, the so-called hot Jupiters that shouldn't exist, be any model of planetary formation that anyone had. And then, as the decades passed, as telescopes improved, as the data accumulated, more and more worlds, each stranger than the last, each more impossible than what came before. The universe does not follow our expectations. It follows only physics, and physics, given enough space, enough time, enough variety of conditions, produces things that no human mind would have predicted if you had asked. Before we looked, tonight we look how we find planets around other stars, the instruments of discovery. Before we can visit the strange worlds, we have to understand how we found them, because the method of discovery tells us a lot about what kind of planet we're looking at and why certain kinds were found before others. Stars are bright, enormously bright compared to any planet. The Sunday, compared to the Earth, is about 1 billion times brighter. Seeing a planet next to a star is like trying to see a firefly next to a lighthouse from a kilometer away, directly imaging planets around other stars, is therefore very difficult, possible in certain gas, with specific techniques, but hard. Most exoplanets have been found by indirect methods, detecting the effect of the planet on the star rather than the planet itself. The transit method, the most productive method for finding exoplanets, is the transit method when a planet passes between us and its star. During its orbit, it blocks a small fraction of the star's light. The star appears slightly dimmer for the duration of the transit. The amount of dimming tells you the size of the planet relative to the star. A large planet blocks more light, a small planet blocks less. The duration of the transit and the period between transits tell you the size of the orbit and therefore the orbital period, the length of the planet's year. The transit method requires that the planet's orbit be aligned, almost exactly edge on to our line of sight, so that it passes across the face of the star as seen from Earth. This is a specific geometric alignment that only occurs for a small fraction of planet-star systems. But the Kepler Space Telescope, launched in 2009, watched more than 150,000 stars simultaneously for 4 years, looking for transit signals. The result was extraordinary. Kepler discovered more than 2,600 confirmed exoplanets and identified thousands more candidates, revolutionizing our understanding of how common planets are and how diverse. The radial velocity method, before Kepler, the primary method for finding exoplanets, was the radial velocity method, also called the Doppler spectroscopy. A planet orbiting a star does not simply orbit the star center. Both the planet and the star orbit their common center of mass, the barycenter. For a massive planet like Jupiter, the barycenter of the Jupiter-Sun system is just outside the surface of the Sunday. The Sun wobbles slightly as Jupiter orbits, moving toward and away from us by a few meters per second as it orbits the barycenter. This wobble changes the wavelength of the light we receive from the star very slightly when the star is moving toward us. Its light is blue shifted slightly when it moves away, red shifted by measuring these tiny shifts in the star spectrum with very sensitive instruments. Astronomers can detect the wobble and from the wobble infer the presence, minimum mass, and the orbital period of the planet. This method is most sensitive to massive planets close to the star because those planets cause the largest and fastest wobble. This is one reason why hot Jupiters were among the first exoplanets found. Direct imaging for very large planets far from their stars. Direct imaging is sometimes possible using special instruments called coronagraphs that block the light of the central star to reveal fainter objects nearby, and advanced adaptive optics, systems that correct in real time for the blurring effect of Earth's atmosphere. Direct imaging has found some extraordinary planets, including some that will appear later in this documentary, planets so large and so far from their stars that their own thermal glow makes them visible in infrared light, what we've found as of 2024. More than 5,500 confirmed exoplanets have been found around other stars. The count grows every month. What this population reveals is extraordinary. Planets are common. Nearly every star may have planets. Our galaxy alone may contain hundreds of billions of planets, but the distribution of planet types is not what we expected. There are more super-Earths, planets larger than Earth, but smaller than Neptune, than any other type. There are very few planets the size of Earth that orbit in the habitable zone of a sun-like star at the right distance for liquid water. There are many very close to their stars in short period orbits that the models didn't predict. The universe has surprised us consistently, thoroughly, and delightfully. Hot Jupiters, the first shock, the first confirmed planet around the sun-like star, was discovered in 1995 by Michel Mayor and Didier Queloz, using the radial velocity method at the Haute-Provence Observatory. In France, the planet Limopoulos-Hatu Pegasi b, later nicknamed Dimidium, was a gas giant, about half the mass of Jupiter, orbiting its star at a distance of 0.052 astronomical units. One astronomical unit is the Earth-Sun distance. 0.052 astronomical units is about 5% of that, about 7.8 million kilometers from its star, while Mercury, the innermost planet of our solar system, is 58 million kilometers from the Sunday. Limopoulos-Hatu Pegasi b orbits its star at 1/7 of Mercury's distance from the Sunday in a year that lasts only 4.23 Earth days. The surface temperature of Limopoulos-Hatu Pegasi b is approximately 1,200 to 1,300 degrees Celsius, hot enough to vaporize most metals. Mayor and Queloz were astonished. Their first reaction was that the measurement must be wrong. They checked it again and again before publishing, and other astronomers, when they first heard the result, were skeptical. Gas giant forming so close to a star made no sense in any model of planetary formation that anyone had. At the time, why hot Jupiters confused everyone. In the standard model of how planetary systems form, gas giants cannot form close to their star. Planets form from the protoplanetary disk, the rotating disk of gas and dust that surrounds a young star. Close to the star, the temperature is too high for ice to exist, and ice, the frozen water and methane and ammonia of the outer disk, is crucial for building the solid cores of giant planets. The core needs to grow to about 10 Earth masses to begin accreting the large envelope of hydrogen and helium that makes a gas giant. Without ice, close to the star, there isn't enough solid material to build such a large core. The gas giant cannot form there. So Limopusatu Pagasi Bay shouldn't be where it is. The only explanation that makes sense is that it didn't form there. It formed far from its star, beyond the snow line, where ice was plentiful, and then through a process called planetary migration, it moved inward, closer and closer to the star until it settled in its current orbit 4.23 days from its star. What causes planetary migration? Newly formed planets interact gravitationally with the surrounding protoplanetary disk. These interactions can cause the planet to lose or gain orbital energy and spiral inward or outward, depending on the specific dynamics. A gas giant forming in the outer disk can spiral inward over millions of years as it interacts with the surrounding gas, losing energy to the disk and moving closer to the star. Migration stops when the disk dissipates, when the young star's radiation blows away the remaining gas of the disk, and the planet is stranded wherever it happens to be. At that point, if migration happens at the right time, the planet ends up very close to the star, a hot Jupiter. If it stops earlier, the planet remains at a more moderate distance, a warm Jupiter. This process now explains the hot Jupiters that was so puzzling in 1995. But it raised new questions. What happened to the inner planets of these systems as the giant migrated inward? Did it destroy them, push them into the star? The evidence suggests that hot Jupiter systems tend to have fewer small inner planets than systems without hot Jupiters, supporting the idea that the migrating giant disrupted or destroyed inner planets on its way in. Hot Jupiters, maybe the survivors of planetary genocide, the giants that swept through their systems, destroying or ejecting whatever was in the way before settling in their final close orbit, WASP 1-2b, the planet being devoured, a world at the edge of existence among the many hot Jupiters found since 1995. WASP 12b is perhaps the most dramatic, the most tragic, if a planet can be, tragic. WASP 12b is about 1,400 light years from Earth. It orbits its host star at a distance of only 3.4 million kilometers, less than 3% of the Earth-Sun distance. In an orbit that takes just 26 hours. 1 year on WASP 1-2b lasts 26 Earth hours. At that distance, the gravitational force of the star on the planet is extraordinary. And because the gravitational force varies with distance, the side of the planet facing the star experiences a much stronger gravitational pull than the far side. This creates tidal forces that stretch the planet into an egg shape, elongated toward and away from the star, not the spherical shape of most planets, and the star is literally pulling material off the planet's surface. The outer atmosphere of WASP 12b is being stripped away, flowing toward the star in a stream of gas that can be observed in ultraviolet light. WASP 12 is losing mass at the rate of approximately 6 times 10 to the power of 11 grams per second, 600 million tonnes per second. That sounds enormous, but the planet is enormous too, about 1.4 times the mass of Jupiter. A Jupiter mass is about 2 times 10 to the power of 30 grams. At the current rate, WASP 12b will lose all its mass in approximately 10 million years, a brief lifespan for a planet, but wait, 10 million years is still a very long time. On human scales, the planet has probably been losing mass for millions of years already. It may have been significantly more massive when it first settled in its current orbit. The end will not be dramatic in the way that the supernova is dramatic. It will simply thin and thin and thin as the star slowly consumes its atmosphere, and eventually whatever solid core remains will spiral inward and merge with the star. We are seeing a planet at the end of its life, its final few million years of existence. The temperature, WASP 12b's dayside, has a temperature of approximately 2,600 degrees Celsius, making it one of the hottest known exoplanets. At this temperature, molecules are ripped apart. Even water, the most stable of common molecules, cannot survive. The dayside, the energy flux from the star is so intense that the planet glows. In infrared, a faint but measurable thermal emission from its own heat that astronomers can detect when the planet passes behind the star. And the combined star plus planet light briefly drops slightly as the planet is blocked. HD 189733b, where it rains glass, a world of blue horror. HD 189733b is one of the best studied of all exoplanets because it transits a relatively bright nearby star, only about 64 light years away. It is a hot Jupiter, somewhat larger than Jupiter, orbiting its orange dwarf star in about 2.2 days at a distance of only 4.8 million kilometers. And it looks blue, a deep, intense cobalt blue, not the blue of Earth from space. Earth looks blue because of its oceans and its atmosphere scattering sunlight. HD 18973333 looks blue because its atmosphere contient silicate particle, glass, tiny, microscopic particles of glass that scatter blue light the same way Earth's atmosphere scatters blue light from the sun. Those silicate particles are not just floating in the atmosphere, they are moving extremely fast The winds on HD 189733b reach speeds of approximately 8,700 kilometers per hour, more than 7 times the speed of sound, and those winds are carrying the silicate particles laterally around the planet in violent storms, powered by the enormous temperature difference between the blazing day side and the cooler night side. The silicate particles in those winds are glass, rain, or glass, driven horizontally at 8,700 kilometers per hour. If you were somehow standing on HD Diplamban 733, which you couldn't because the surface conditions would be instantly lethal. But if you could, the glass would sandblast you at supersonic speeds. Instantly, the dayside temperature is about 1,200 degrees Celsius. The night side, about 1,000 degrees Celsius. The difference between the two sides is only about 200 degrees. Despite the extreme temperature difference you might expect between the sunlit and dark sides, the winds are responsible for this. The violent, supersonic, silicate-laden winds efficiently transport heat from the day side to the night side, equalizing the temperature across the planet. This heat redistribution by the atmosphere is one of the most important features of hot Jupiter atmospheres, and studying it in detail on planets like Hodea 89733 teaches astronomers about atmospheric dynamics in conditions far more extreme than anything in our solar system. TRES 2b, the darkest world, blacker than black, TRES 2b, discovered in 2006 by the Transatlantic Exoplanet Survey, about 750 light years away. It is a gas giant, about 1.2 times the mass of Jupiter, orbiting very close to its star with a period of about 2.5 days, and it is the darkest known planet in the universe. TRES 2 reflects less than 1% of the light that hits it, less than 1%. For comparison, coal, one of the darkest common substances on Earth, reflects about 4% of light. TRES 2b is darker than coal, darker than any paint, darker than any artificially created dark material, almost entirely absorbing all light that hits it. It is almost perfectly black. Why? What makes a planet this dark? The answer is still not completely understood. It doesn't have the thick cloud layers of molecules like sodium and potassium that reflect light in Jupiter and Saturn. In our solar system, its atmosphere contient vapor of light-absorbing chemicals, including vaporized sodium, potassium, and possibly titanium oxide and vanadium oxide, all of which are extremely good at absorbing light rather than reflecting it. The combination of these absorbers in a very hot, very low albedo atmosphere produces a planet that absorbs almost all of the starlight that reaches it, converting it to heat rather than reflecting it back into space Strangest is not completely invisible. It emits a faint red glow from its own heat. Its day side at about 1,500 degrees Celsius glows dimly in infrared and at the very edge of the red part of the visible spectrum, a dim, barely perceptible red glow, like a piece of cooling metal in the dark, but reflecting light from its star, almost not at all. The darkest world that we know of in the universe, a planet that doesn't want to be seen, 55 Cancri A, the diamond planet, a world of crystal. 55 Cancri is a super Earth, about 8 times the mass of our planet, orbiting the star 55 Cancri A, about 41 light years from Earth. It orbits extremely close to its star at a distance of only 2.4 million kilometers, completing its orbit in just 17.8 hours. 1 year on 55 Cancri E lasts less than 18 hours. The temperatures on its surface are approximately 2,000 to 2,700 degrees Celsius. On the day side, hot enough to melt almost any known material. But what makes 55 Cancri E extraordinary is what it is made of. The star 55 Cancri A has an unusually high carbon to oxygen ratio, much higher than our Sunday. When the protoplanetary disk of this star formed, the high carbon content changed what chemistry was possible in the forming planets, where a solar system like ours forms planets with oxygen-dominated minerals, silicates, iron oxides, the minerals of Earth and the other rocky planets. A carbon-rich disk forms very different materials. In a carbon-rich environment, instead of silicates, you get carbides, silicon carbide, instead of silica, and instead of iron oxide, pure carbon, in its most stable crystalline form. At high pressure, diamond, models of 55 Cancri E, suggest that its interior contains a significant fraction of carbon, much of it in the form of diamond, under the enormous pressure of the overlying rock, potentially a diamond layer or mantle surrounding an iron core with a graphite surface. Above the diamond, the total mass of diamond in 55 Cancri E has been estimated at perhaps 1/3 of the planet's total mass for an 8 Earth mass planet. That is roughly 3 Earth masses of diamond, a diamond planet, 8 times the mass of Earth. 17 Urorbit, 2,700 degrees on the surface, 41 light years away. I should note that this interpretation has been challenged. More recent observations suggest that 55 Cancri E may have a volatile atmosphere, and its composition may be more complex than the simple diamond model. But even in revised models, it remains one of the most extraordinary super-Earths known, with conditions far beyond anything. In our solar system, Kepler 16b, the Tatooine world, a planet with 2 suns in the original Star Wars film, Luke Skywalker, stands on the desert planet Tatooine and watches a double sunset, two suns setting simultaneously on the horizon. Scientists at the time considered this scientifically dubious. Planets in binary star systems, that is, systems with two stars, were thought unlikely to form or to have stable orbits. In 2011, the Kepler Space Telescope found Kepler-on and changed the conversation. Kepler-on is a gas giant about the mass of Saturn, orbiting two stars simultaneously in a circumbinary orbit, an orbit that goes around both stars. At once, the two stars, Kepler-on and Kepler-on, are both smaller and cooler than our Sunday, and they orbit each other in about 41 days. Kepler-on orbits the pair of stars once every 229 days at a distance that puts it just inside the outer edge of the habitable zone, though it is a gas giant and not a place where life as we know it could survive. Standing on a moon of Kepler-on, if such a moon existed, you would see two suns in the sky, a larger orange-yellow one and a smaller, redder one, moving relative to each other over the course of their 1-day mutual orbit. The view would be extraordinary. Sometimes the two stars would be close together in the sky, nearly touching, their combined light bright. Sometimes they would be separated by a significant angle, two distinct, different colored suns in the same sky. Science fiction imagined this before science found it, and when science found it, the scientists at the press conference for the discovery showed a clip of the Luke Skywalker sunset from Star Wars to illustrate what they had found. Other circumbinary planets, Kepler-on was the first confirmed circumbinary planet, but it was not the last. Several more have been found by Kepler and by subsequent missions. Kepler-34, Kepler-35, Kepler-38, Kepler-47 and 47, and others circumbinary planets are apparently not rare. They can form and exist in stable orbits around binary stars. The planetary science that assumed otherwise had to be revised. The universe allowed something that we thought was too complicated, too dynamically unstable to work. It didn't care about our models. It just made the planets EA 504, the magenta planet, a world the color of a rose. Gaia Utsaznij, discovered in 2013 by direct imaging from the Subaru telescope. In Hawaii, it orbits the star GJ 504 about 57 light years from Earth at a distance of about 43.5 astronomical units, 9 times the Earth-Sun distance. At that distance, the orbital period is estimated at about 160 years. A year on GJ Utsaznij lasts 160 Earth years. The planet is about 4 times the mass of Jupiter making it a super Jupiter on the boundary between a very large planet and a brown dwarf. The smallest failed stars. What makes GJ 504b distinctive is its color, being young, about 160 million years old. The planet still retains the heat of its formation. It has not yet cooled significantly from the energy released when its mass collapsed under gravity into a planet. Its atmosphere at a temperature of about 237 degrees Celsius, cool enough for methane to form in the upper layers. The combination of temperature and atmospheric chemistry gives GJ 504 a color unlike almost any other planet. Magenta, a deep pink magenta color, like a cherry blossom or a deep rose. It is not pink in the way that Mars is red from iron oxide. It is pink from its temperature and chemistry, the infrared glow of a young, still warm planet, combined with the spectral absorption of methane, producing a color that astronomers described as magenta or cherry blossom pink, a magenta planet larger than Jupiter, orbiting far from its star, still glowing with the heat of its formation 160 million years. After it formed, the formation problem, GJ 8008, creates a problem for models of planet formation. Giant planets at 43 astronomical units from their star are difficult to explain with standard models. The core accretion model, the standard explanation for how gas giants form, works by building a solid core from the solid material of the protoplanetary disk and then accreting an envelope of gas. But at 43 AU, the disk is so diffuse that building a core large enough to trigger rapid gas accretion in the available time before the disk dissipates is very difficult. An alternative is gravitational instability. The disk itself becoming unstable and fragmenting directly into a massive object without the need for a solid core to form first. But this mechanism also has difficulties at Batuzeci 3O in a system with the mass of the GJ 504 system. GJ 8008 may require a modified or new formation model to explain how it got where it is. One more puzzle for planetary science to solve: rogue planets, worlds without stars. Not all planets orbit stars. There are planets in the universe that are not attached to any star, that drift through the galaxy alone in the dark, without a sun, without warmth, without any of the things that we associate with a planet's existence. These are called rogue planets, or free-floating planets, or orphan planets. They are not hypothetical. We have found them several by different methods how rogue planets form. There are two main mechanisms by which a planet can be ejected from its parent system and become a rogue. The first is gravitational ejection. In the chaotic early history of a planetary system, multiple planets interact gravitationally with each other and with the young star in complex, unpredictable ways. Sometimes one planet comes close to another and gains energy from the interaction, gaining enough velocity to escape the gravitational well of the star and fly off into interstellar space, free. The other planet in this exchange loses energy and falls into a closer orbit, perhaps becoming a hot Jupiter. As a result, the ejection of planets during the early chaotic period of a solar system's history may be common. Some models suggest that our own solar system ejected several giant planets in its early history before settling into the relatively ordered arrangement we see today. The second mechanism is formation in isolation. Some of the smallest rogue planets may have formed not in a protoplanetary disk, but directly from the collapse of a small cloud of gas and dust in interstellar space, in the same way that a star forms but with too little mass to ignite fusion, too small to be a star, too large to be an asteroid, a planet formed in isolation from the beginning without ever having a parent star. How we find rogue planets by definition do not orbit a star, so the transit method cannot work. The radial velocity method cannot work. They don't have a star to affect. The main method is gravitational microlensing. When any massive object passes between us and a more distant star, its gravity acts as a lens, bending and focusing the light from the distant star, brightening it temporarily. The shape and duration of the brightening depends on the mass and velocity of the lensing object. For a planet mass object, the brightening is brief, perhaps days. For a stellar mass object, weeks or months. Surveys that monitor millions of stars for microlensing events occasionally detect brief planet mass lensing events with no associated stellar lens, indicating a free-floating planet mass object. Several such events have been detected, suggesting that rogue planets are not rare. Some estimates suggest that there are more rogue planets in the Milky Way than there are stars. If true, the galaxy is filled with billions of cold, dark, lonely worlds drifting through the interstellar void without any sun. What a rogue planet is like. A rogue planet, far from any star, is cold, very cold. The surface temperature of a small, rocky, rogue planet might be a few tens of degrees above absolute zero, perhaps minus 230 degrees Celsius. A cola without sunlight, there is no photosynthesis, no energy input to power a surface biosphere, but there is geothermal energy from the radioactive decay of elements in the planet's interior and from the residual heat of formation. A larger rogue planet might have a liquid water ocean under a thick ice shell kept liquid by internal heat in the same way that Europa, Jupiter's moon, has a liquid ocean under its ice kept liquid by tidal heating from Jupiter. On a rogue planet, the ocean would be kept liquid by internal geothermal heat rather than tidal heating. But the principle is the same. Some astrobiologists have speculated that rogue planets with thick ice shells protecting liquid water oceans warmed by internal heat and perhaps hydrothermal vents on the seafloor could harbor life in the deep, in the warmth, in the chemical richness of the volcanic seafloor, even far from any star, even in the cold, dark, interstellar void, super Earths and ocean worlds, the most common unknown planet type. There are no super Earths in our solar system. This is strange because super Earths, planets larger than Earth but smaller than Neptune, are the most common type of planet that Kepler found around other stars. Why do we not have one? We don't know. Our solar system is unusual in this respect, having a gap in planet sizes between Earth at 1 Earth mass and Neptune at 17 Earth masses, while most other systems have planets in that range. Super Earths are a diverse category, ranging from 1.5 to about 10 Earth masses, and covering an enormous range of composition and conditions. Some super Earths are thought to be rocky like Earth but larger, with thicker crusts, more massive interiors, perhaps more volcanism, perhaps different plate tectonics. Some may be ocean worlds with global world-spanning oceans of water, hundreds of kilometers deep, with no dry land. Anywhere, just water, ocean, all the way down to the mantle. An ocean world 100 times the depth of the deepest ocean trench on Earth, the Mariana Trench, in 9 kilometers. An ocean world super Earth might have oceans even 1,000 kilometers deep. At those depths, the pressure is so extreme that water cannot remain liquid. In the normal sense, it transitions to exotic forms of ice called high-pressure ice, ice Zibbe, ice X, crystalline structures of water molecules under extraordinary compression. An ocean world at the very deepest levels may have a layer of high-pressure ice sitting on top of the rocky mantle of the planet, with liquid water above that ice, and above the liquid water, more ice, a frozen crust, and above that, perhaps atmosphere. The chemistry of such a world would be dominated by water. The minerals of the rocky mantle would not be in contact with the ocean because the high-pressure ice forms a barrier between them. The ocean would not have the mineral input from the seafloor that Earth's ocean has from hydrothermal vents. Could life exist in such a world without the minerals from hydrothermal vents? The chemistry of an ocean world may not have the diverse, specific chemical inputs that life as we know it depends on the answer is genuinely uncertain. Specific super-Earth worlds, Kepler-Irmik, one of the first potentially habitable exoplanets found by Kepler, about 2.4 times Earth's radius, orbiting in the habitable zone of a sun-like star, about 620 light-years away. Its composition is unknown. It could be rocky, water-rich, or even a mini gas giant. We don't have the measurements to distinguish between these possibilities yet. Geye ezerkit sastizennej, sometimes called a water world or ocean world, about 2.7 times Earth's radius, with a density too low for pure rock, consistent with a large water fraction, a thick, steam-rich atmosphere, and possibly a deep ocean orbiting a small red dwarf star only 40 light-years from Earth, one of the most studied super-Earths. Pulsar planets orbiting dead stars in 1992, Alexander Wolszczan and Dale Frail announced the discovery of planets orbiting a pulsar Psiar 1200 MTU plus 12, about 2,300 light-years from Earth. It was the first confirmed detection of planets outside our solar system before 51 Pegasi b, before the era of hot Jupiters, and it was completely unexpected. A pulsar is the remnant of a massive star that exploded in a supernova. The explosion is one of the most violent events in the universe, releasing more energy in seconds than the sun will produce in its entire lifetime. Any planet that was orbiting the star before the supernova would be expected to be destroyed by the blast, or at least stripped of its atmosphere and bombarded by lethal radiation. And if it survived, it would lose the gravitational anchor of its star as the star loses most of its mass in the explosion and fly off into interstellar space. How could planets be found around the pulsar? Wolszczan and Frail detected the planets through the extraordinarily precise timing of pulsar pulses. Pulsars rotate many times per second, emitting beams of radio waves that sweep past us, like a cosmic lighthouse with extraordinary regularity. If a planet is orbiting the pulsar wobbles slightly in its orbit around the system's barycenter, and this wobble causes tiny but measurable variation in the timing of the pulsar pulses arriving at Earth. The timing of pulsars is so precise that it can detect wobbles that would be entirely undetectable by any other method. Wolszczan and Frail found 3 planets around PSR 1257 plus 12, 2 approximately Earth mass and 1 smaller, moon-sized. What pulsar planets are like. The environment around a pulsar is not hospitable. Pulsars emit intense beams of electromagnetic radiation in the radio, and sometimes X-ray ranges, and a powerful wind of high energy particles, the pulsar wind, any atmosphere that a planet might have would be stripped away by the pulsar wind. Over time, the surface would be bombarded by radiation that would sterilize any surface life. Immediately, these are perhaps the most hostile environments for any planet in the universe. Irradiated, bombarded, stripped of atmosphere by the remnant of a violent explosion. How did they form? There are two possibilities. The first is that the planets survived the supernova, somehow stripped of their atmospheres. Their orbits changed by the loss of the star's mass, but surviving as solid bodies, gradually settling into new stable orbits around the pulsar. The second, and perhaps more likely, is that the planets formed after the supernova from the disk of material that can sometimes accumulate around the pulsar from the fallback of supernova debris, or from the disruption of a companion star in a second generation of planet formation, from the ashes of the explosion that created the pulsar. If the second scenario is right, these are truly post-apocalyptic worlds born from the ruins of a stellar explosion formed in a disk around a dead star, worlds that rose from the ashes of destruction. The oldest known planet, a world from the beginning of time, PSR, B1620,6 nicknamed Methuselah, after the biblical figure famous for his extreme longevity, is the oldest known planet in the universe. Its age is estimated at approximately 12.7 billion years. The universe itself is 13.8 billion years old. This planet formed only about 1 billion years. After the Big Bang, it orbits not one star, but a binary system, a pulsar, and a white dwarf in the globular cluster, Messier 4, about 5,600 light years from Earth. This is extraordinary on multiple levels. At 12.7 billion years old, this planet has been orbiting through the entire history of the galaxy. It was already old. When Earth formed, it was already old. When the sun ignited, it has been in the universe for 12 times the current age of our planet. When this planet first formed, the universe was very different. The first generation of stars was still burning. The first heavy elements were only just being forged in stellar interiors. The Milky Way was young, still forming, still irregular, not yet the spiral galaxy we inhabit today, and somehow from that ancient early universe, a planet formed and survived for 12.7 billion years through the death of its original star, which became the white dwarf in the binary system through the merger with the pulsar. Through 12.7 billion years of the galaxy's evolution, it is still there, still orbiting, still following the laws of physics in an orbit that has persisted for almost the entire history of the universe. if there were a world where memory could last that long, the memory of 12.7 billion years would be unimaginable. Those planets that orbit backwards, retrograde worlds in our solar system, all the planets orbit the Sunday in the same direction, counterclockwise, when viewed from above the North Pole. This makes sense because they all formed from the same protoplanetary disk, which was rotating in a specific direction, and the planets inherited that rotational direction, but some exoplanets orbit their stars in the opposite direction from the star's rotation, retrograde. Backward, several hot Jupiters have been found en retrograde orbis was 17b. One of the most studied is on a retrograde, and also extremely tilted orbit. This is, according to standard models, impossible. If a planet forms in a protoplanetary disk, it should orbit in the same direction as the disk, as the star, always. So how did these planets get onto retrograde orbits? The answer, again, is migration, but a more violent kind. Instead of the gentle, disk-driven migration that creates normal hot Jupiters, retrograde hot Jupiters may have been put on their current orbits by gravitational interactions with other planets or with a distant stellar companion. The Kozai-Lidov mechanism, a gravitational interaction between a planet and a distant companion, can cause the planet's orbit to become highly inclined and highly eccentric over millions of years, and then tidal interactions with the star at the closest approach in the eccentric orbit can shrink the orbit and circularize it, leaving the planet in a close circular orbit, but at the high inclination or even retrograde inclination that the Kozai-Lidov mechanism gave it. Retrograde hot Jupiters are evidence of a violent, chaotic, gravitational history of the planetary systems, worlds that were thrown into their current extreme backward orbits by gravitational catastrophe. The universe as a laboratory, what strange planets teach us. Let me step back from the specific planets and think about what all of this actually means. The discovery of exoplanets has transformed planetary science in a very specific way. Before exoplanets were held one data point, our solar system, 8 planets, 1 star, 1 arrangement. That was all. We knew from one data point. You cannot draw general conclusions. You cannot know whether what you have is typical or extraordinary, rare or common, the norm or the exception. Now we have thousands of data points, thousands of planetary systems in various configurations at various distances around various kinds of stars. And the picture that emerges is humbling. Our solar system is not typical. Typical is not what we have. The typical star may have a super-Earth or a mini-Neptune in a close orbit, not an Earth, and a Jupiter. In the places that we have them. The typical planetary system may be more compact than ours, with more planets closer to the star. Oh, with its planets spread over 30 AU, maybe relatively unusual, and the strange worlds, the hot Jupiters, the retrograde planets, the diamond super-Earths, the iron rain worlds, the rogue planets are not anomalies to be explained and then ignored. They are the universe telling us what it is capable of, what range of outcomes physics allows given the right conditions. The universe is a laboratory running experiments in planetary science at scales and in conditions that no human laboratory could replicate, and the experiments, the planets, are the results for us to read and learn from. Every strange planet, every impossible world that contradicts our prior expectations is an invitation to revise our understanding of how things work. And that is the most important thing that science does. The closing part one, the universe does what it wants. We have visited worlds tonight that should not exist. A planet where it rains iron, a planet darker than coal, a planet made partly of diamond, a planet orbiting two suns, magenta planets, retrograde planets, worlds without stars, the oldest planet in the universe, worlds being devoured by their own stars, worlds of glass, and acid winds and silicate rain, all of them real, all of them measured, all of them the products of physics operating in conditions different from what we know, producing outcomes that no one predicted before the telescopes found them. The universe does not consult our expectations before deciding what to do. It follows the rules, its own rules. Physics, given enough variety of initial conditions, produces an astonishing range of outcomes. The Iron Rain planet is not a science fiction invention. It is physics applied to a hot, tidally locked atmosphere. The result is Iron Rain. The darkest planet is not an artistic choice. It is physics applied to a hot atmosphere with specific light-absorbing chemicals. The result is near perfect blackness. The diamond planet is not a metaphor. It is chemistry in a carbon-rich, high-pressure environment. The result is diamond. Everything follows from the conditions, from the physics. No design needed, no intelligence needed, just the right conditions. And the laws of nature do the rest. And there are thousands more worlds we haven't visited. Tonight, thousands of confirmed exoplanets waiting to be described in detail. Millions more, almost certainly out there, undetected, waiting to be found. The universe has been making planets for 13.8 billion years. It has had a lot of practice, and it is extraordinarily creative. Let your breathing slow. Let the world settle around you. The iron rain falling on a tidally locked ocean of vaporized metal 640 light years away. The darkest world, absorbing everything in silence 750 light years away. The diamond interior of 55 cancri under 2,700 degrees, 41 light years away. The twin sun sunset on Kepler-16, 200 light years away. These are real places in the real universe existing right now, following the laws of physics without any knowledge that anyone on a small rocky planet 600 og 4 og 700 og 50 og 41 og 200 light years away was thinking about them tonight. Rest now. The universe will keep making strange worlds while you sleep. It has been doing it for 13.8 billion years, and it shows no sign of stopping. Before we continue tonight, I wanted to remember where we left off. We visited worlds that should not exist. A planet where it rains iron, a world darker than coal, a planet partly made of diamond, a world orbiting two suns, a magenta planet still glowing from the heat of its formation, rogue planets drifting alone in the dark between the stars without any sun at all. And we ended with a thought that the universe does not consult our expectations before deciding what to do. Tonight, we continue. There are more worlds to visit, some stranger than what we've already seen, some quieter, some that raise the deepest question that any of these worlds can raise. Are we alone? We're not going to answer that tonight because no one can yet, but we're going to get as close as the evidence allows. And then at the end, we're going to come home the way we always do, back to this room, this planet, this particular ordinary, extraordinary night. Tell me where in the world you are right now, what country, what city, what time. Drop it in the comments before you fall asleep. Now, let's go back out into the atmospheres of other worlds, reading the air from light years away. Before we visit more specific planets, I want to explain something remarkable about how we study them. We cannot travel to exoplanets. The nearest one is 4.2 light years away at the speed of our fastest spacecraft. It would take about 80,000 years to reach it, and yet we know what some exoplanet atmospheres are made of. We can read the chemistry of a planet's air from billions of kilometers away without going there, without sending anything, just by watching the starlight very carefully. Transmission spectroscopy, when a planet transits its star, passes in front of it, some of the starlight passes through the planet's atmosphere. At the edges of the planet's disk, the atmosphere is not a perfect blocker. It is partly transparent, and different gases in the atmosphere absorb different specific wavelengths of the passing starlight. By comparing the spectrum of the star when the planet is not in front of it to the spectrum when the planet is transiting, astronomers can see which wavelengths are absorbed more during the transit. Each absorbed wavelength is a fingerprint, a specific signature of a specific molecule. Water vapor absorbs at certain wavelengths carbon dioxide, at others methane, sodium, potassium, H1 identifiable. In the spectrum, this is called transmission spectroscopy, and it has revealed the chemical composition of dozens of exoplanet atmospheres, including some of the most extreme and unusual chemistry in the universe. The James Webb Space Telescope, with its extraordinary infrared sensitivity, has transformed atmospheric science for exoplanets, detecting molecules in exoplanet atmospheres with a precision that was impossible before its launch. What we found in exoplanet atmospheres is a zoo of chemistry, sodium at thousands of degrees, in hot Jupiters, water vapor, in dozens of atmospheres, carbon dioxide, carbon monoxide, methane, ammonia, hydrogen cyanide, sulfur dioxide, detected in the atmosphere of WASP 39b, a hot Saturn 700 light years away. The molecules of the universe writing themselves in starlight from hundreds of light years away. For us to read WASP 76b revisited the Iron Rain world in detail, we began our journey in the first part with WASP 76b, the planet where it rains iron. Let me take you deeper into that world. Now that we understand atmospheric spectroscopy, WASP 2b, 640 light years away, orbits its star in 1.8 Earth days, tidally locked. One face always toward the star, one face always away. The dayside temperature, approximately 2,400 degrees Celsius. At this temperature, iron, which melts on Earth at 1,538 degrees, does not just melt, it vaporizes. It becomes iron gas, rising in enormous atmospheric convection, currents driven by the intense heating. From the star, the iron vapor, carried by powerful winds, moves from the dayside toward the terminator, the boundary between the permanent day and the permanent night, and into the night side, where temperatures drop to around 1,400 degrees Celsius, cool enough for iron vapor to condense back into liquid, iron droplets falling as rain. The detection of iron rain on WASP 2b was made using the espresso spectrograph at the Very Large Telescope in Chile. By measuring the spectrum of the starlight as the planet transited, they detected iron vapor on the leading edge of the planet, the edge moving into the star's light as the planet orbits, but not on the trailing edge, the edge moving away from the starlight. This asymmetry, this difference between the two edges of the transiting planet, is exactly what you would expect if iron vapor rises on the dayside, moves over the terminator, and condenses, rinds out on the night side, so that the trailing edge of the planet as it passes in front of the star, has already rained out its iron and contain less iron vapor than the leading edge, a signature of iron rain, written in starlight from 640 light years away in a single transit lasting a few hours, what the iron rain would look like if you were somehow standing on the terminator of WASP 76b, which you couldn't. But imagining the sky above you would be perpetually dramatic. To your day side, an enormous star, 25 times larger, in the sky than our sun appears. From Earth, blazing, filling a quarter of the visible sky at surface temperatures of 6,250 degrees. The air around you, scorching, unbreathable, thick with iron vapor, rising from below, above iron clouds, denser, dark, moving with the planetary wind toward the night side, and falling from those clouds, not water droplets, not ice crystals, but liquid iron, molten metal, falling in droplets from the iron clouds, the size of raindrops, but made of metal, at 1,400 degrees Celsius, each one glowing faintly red-orange, like tiny falling embers from the iron clouds above, and the ground, whatever the ground is, on such a world, perhaps an ocean of liquid rock or some form of liquid metal being struck continuously by iron rain from above. This is a real place in the real universe, 640 light years away, and it is like this right now while you listen. K2, Stratus Patsatu B, the lava ocean world, K2, Satu Patsatu B, discovered by the Kepler telescope about 202 light years from Earth. It is a super Earth, about 1.5 times Earth's size and 5 times Earth's mass. It orbits its host star in just 6.7 Earth hours, one of the shortest orbital periods of any confirmed rocky planet, 6.7 hours. 1 year on K2 141b lasts less than an Earth working day. The implications of this orbit are extreme. Like WASP, successive the B, K2 141b is tidally locked, one face always toward the star. The dayside temperature is approximately 3,000 degrees Celsius, hot enough to vaporize rock, not just melt it, vaporize, to turn solid stone into gas. The dayside of K2 141b is covered in an ocean of lava, molten rock, liquid stone, hundreds of kilometers deep. An ocean, not of water, but of magma, stretching across the entire sunlit face of the planet. Above the lava ocean, a rock atmosphere, rocks that we would think of as solid, as permanent features of a planet's surface. Are here gas, vapor, rising from the boiling lava ocean into the superheated sky. The atmosphere of K2 141b is made of vaporized rock, mineral vapor, silicon monoxide, sodium, silicon dioxide, the stuff that granite and sandstone and the crust of the earth are made of floating as gas in the sky of K2141b. Predictions. Mols of K200 or Innerfjord suggest that the mineral vapor in the atmosphere is carried by supersonic winds toward the night side, where temperatures drop dramatically and the mineral vapor condenses and falls as rock rain, rock snow, mineral precipitation on a world where rock is the equivalent of water going through its cycle, evaporating on the day side, precipitating on the night side, flowing back on the surface as rivers of lava back to the day side to evaporate again, a rock cycle analogous to the water cycle on Earth, but with rock at 3,000 degrees on a world where lava is the ocean and stone is the rain, Tres Catreb, the planet that shouldn't be solid, Tres Quatreb, discovered in 2007, about 1,700 light years from Earth. It is a gas giant, about 1.7 times the size of Jupiter, one of the largest known exoplanets in terms of radius, but only about 0.9 times Jupiter's mass. Do the math, 1.7 times larger, but slightly less massive than Jupiter. The density of Tres 4b is approximately 0.2 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. Jupiter itself has a density of 1.3 grams per cubic centimeter. Tres Catreb is 1/6 the density of water, about the density of balsa wood, the lightest structural wood used in model aircraft. If you could find an ocean large enough, Tres Catreb would float in it a planet the size of 1.7 Jupiters that would float on water. How? Tres Catreb orbits its star very closely, about 7 million kilometers. Completing an orbit in 3.5 days, the dayside temperature is about 1,700 degrees Celsius. At that temperature, the outer atmosphere expands dramatically, puffed up by the intense heating from the nearby star. The atmosphere is bloated, inflated, stretched to an enormous size by the heat energy deposited by the star. These planets are called inflated hot Jupiters or puffy planets, and Tres Quatrube is one of the puffiest. The inflation is so extreme that the planet may be losing its atmosphere to space as the outermost gas exceeds escape velocity and bleeds off into the planetary environment and eventually to the star. Models suggest that the outer atmosphere of Tres Quatreb may extend into a comet-like tail streaming away from the star as the intense radiation pushes the upper atmosphere into escape or planet, evaporating in real time, puffing up by the heat of its star until its outer layers blow away like smoke into the planetary wind. Kepler-U6n the first truly Earth-sized planet in a habitable zone, in April 2014. The Kepler team announced the discovery of something that the astronomical community had been waiting and hoping and working to find for years Kepler 6 and Alpha, the first confirmed Earth-sized planet orbiting within the habitable zone of another star. Kepler 6 and Alpha is about 500 light years from Earth. It is approximately 1.1 times the radius of Earth, very close to Earth size. It orbits a red dwarf star, Kepler 6 and Alpha, in approximately 130 days, an orbit that places it at the outer edge of the habitable zone, the region around the star where temperatures could allow liquid water to exist on a planet's surface. If the planet has the right atmosphere, it is the fifth and outermost of 5 known planets in the Kepler 6 and Alpha system. The inner 4 are all much closer to the star and much too hot for liquid water, why Kepler 186f matters. Before Kepler 186f, we had found planets in habitable zones, but they were all much larger than Earth, super-Earths, whose compositions were unknown, which might be rocky or might be water-rich ocean worlds or even gas-dominated, mini Neptune, and we had found Earth-sized planets, but none in habitable zones. They were all too close to their stars, too hot. Kepler 6 and Alpha was the first to be both Earth-sized and in the habitable zone, the combination that we'd been looking for, what Kepler 186f might be like. We don't know as much as we'd like about Kepler 186f. We know its size, approximately. We know its orbital period. We know the properties of its star. We don't know its mass without knowing the mass. We can't know the density, and without knowing the density, we can't know whether it's rocky, like Earth, or something else. We don't know whether it has an atmosphere, whether it has water, whether it has anything that would make life as we know it possible. What we know is that it is the right size, in the right place, around the stable star. The star Kepler 6 and Alpha is a red dwarf, smaller and cooler than our Sunday red dwarfs are the most common type of star in the Milky Way. About 70% of all stars are red dwarfs. Red dwarfs live much longer than sun-like stars, potentially trillions of years, much longer than the current age of the universe. A planet orbiting a red dwarf in the habitable zone might have much more time to develop life than Earth has had. If life develops slowly over billions of years, more time is a significant advantage. But red dwarfs also have a significant problem for habitability. They are, in their early years, much more magnetically active than our Sunday, producing powerful flares, bursts of radiation, and charged particles that could strip away the atmospheres of close-in planets before life has a chance to establish itself, and planets in the habitable zone of a red dwarf are much closer to the star than Earth is to the Sunday because red dwarfs are so much dimmer. The habitable zone is much closer in, close enough that the planets may be tidally locked, one face, always toward the star, creating dramatic day-night differences that would challenge life as we know it. Whether red dwarf planets can be habitable is one of the most active debates in astrobiology right now. The answer has profound implications because if they can, the most common stars in the galaxy are also the most common hosts of potentially habitable worlds. TRAPPIST-YXI, 7 worlds around the tiny star. In February 2017, the announcement of the TRAPPIST-1 system generated more excitement in the planetary science community than almost any other exoplanet discovery before or since. TRAPPIST-YXI is a red dwarf star about 39 light years from Earth. It is tiny by stellar standards, about 8% the mass of our Sunday, just barely large enough to Rostein, the nuclear fusion that makes it a star, at the lower edge of stellar possibility, and it has 7 planets, all roughly Earth-sized, all orbiting very close to this tiny Jing red star. 7 worlds, all within the equivalent distance of Mercury's orbit around our Sunday, 3 of them designated TRAPPIST-YXI, TRAPPIST-1, and TRAPPIST-1 are in the habitable zone. 7 potentially rocky, Earth-sized worlds around a single star, 39 light years away. 3 of them in the habitable zone. This was extraordinary. The system, in more detail, the 7 planets, TRAPPIST 1b through H, have orbital periods ranging from about 1.5 days to about 18.8 days. Compared to Earth 365, they are in an unusual configuration called a resonant chain. Their orbital periods are related to each other by simple ratios 4, 2, 1, and so on. This resonant configuration stabilizes the orbits, allowing them to remain in their close, packed arrangement for billions of years. The masses of all 7 planets have been measured from the gravitational effects they have on each other. Each passing planet slightly alters the orbital periods of its neighbors through gravity, and by measuring these variations, the masses can be determined. The masses combined with the sizes give the densities, and the densities areole consistent with rocky compositions similar to Earth, iron cores, silicate mantles, rocky planets, not gas giants, not water worlds. Rocky, TRAPPIST-YXI, the one most similar to Earth in terms of its position in the habitable zone, is also among the most similar in density, about 0.77 Earth masses, about 0.92 Earth radii, a slightly smaller, less massive, but otherwise Earth-like planet at the right distance from its star for liquid water to potentially exist. What we've learned from Webb observations, the James Webb Space Telescope has observed several of the TRAPPIST-1 planets, looking for atmospheres, and the results so far are instructive about the challenges of habitability. TRAPPIST-1b, the innermost planet, appears to have no thick atmosphere. The infrared emission from its day side is consistent with a bare rock with no significant atmosphere to redistribute heat. TRAPPIST-1c. The second planet similarly appears to lack a thick Venus-like carbon dioxide atmosphere. At least these results don't rule out atmospheres on the outer planets, the habitable zone planets, but they suggest that at least some of the inner planets may have lost their atmospheres to the intense early activity of the red dwarf. The search continues for atmospheres on TRAPPIST-1d through 1H, the outer planets that had more protection from the early flares, and that's it, in or near the habitable zone, if any, of those outer planets retains an atmosphere. The TRAPPIST-1 system will be among the most important objects in science, a nearby system of rocky, potentially habitable worlds accessible enough for detailed study within our lifetimes. Proxima Centauri, the nearest exoplanet, the nearest star to our Sunday, is Proxima Centauri, part of the Alpha Centauri triple star system, 4.2 light years away. In 2016, a planet was confirmed orbiting Proxima Centauri. Proxima Centauri b, the nearest known exoplanet to Earth. Proxima Centauri b is at least 1.07 Earth masses, making it a near-Earth mass planet. It orbits in the habitable zone of Proxima Centauri at a distance of about 7.5 million kilometers in an orbital period of about 11.2 days, 4.2 light years away, still impossibly far on human timescales, but closer than any other known exoplanet. The Breakthrough Starshot Initiative, a proposed, though not yet funded or built, space project, has proposed sending a fleet of tiny, gram-mass, laser-sail spacecraft accelerated by powerful lasers on Earth to about 20% of the speed of light. The journey to Proxima Centauri would take about 20 years. The spacecraft would fly through the Proxima system in a fraction of a second, taking images and measurements as they passed, and then transmitting that data back to Earth over the 4-2-year travel time of the signal. We might, within this century, have the first direct image from another star system, from another world, that we know is there what Proxima b might be like. The challenges are similar to TRAPPIST, a red dwarf star. Proxima Centauri is one of the most flare-active red dwarfs known. It regularly produces powerful X-ray flares that would be devastating to any unprotected surface life. If Proxima b has a substantial magnetic field like Earth, which deflects the charged particles of solar wind and flares, it might be protected enough for life to exist on or under the surface or in subsurface oceans. If it doesn't, the surface may be sterile, stripped of any atmosphere, radiated by its active star. We don't know which is the case. We haven't been able to detect an atmosphere on Proxima b, yet the planet does not transit its star from our perspective, so transmission spectroscopy is not possible with current tools. LHS 1140b, the best candidate for a habitable world, if I had to choose today on the exoplanet that astronomers consider the best current candidate for a potentially habitable world. Many would point to LHS 1140b. LHS 1140b is about 41 light years away. It orbits a red dwarf star in about 25 days, placing it in the habitable zone. It is about 1.7 Earth radii and about 5.6 Earth masses, slightly larger and more massive than Earth, but with a density consistent with a rocky composition, perhaps with a significant water content. What makes LHS 1140b particularly interesting is its star. LHS 1140 is one of the quietest, least active red dwarf stars known. It flares rarely and weakly compared to most red dwarfs. This matters enormously for habitability because the major threat to atmospheres on red dwarf planets is the stellar activity, the flares, the X-ray radiation, the charged particle winds. From an active star, a quiet star reduces this threat dramatically. A planet in the habitable zone of a quiet red dwarf has the right distance for liquid water and a star that isn't constantly blasting it. 2024 observation by the James Webb Space Telescope found hints, tantalizing but not yet conclusive, that LHS 1140b might have an atmosphere, specifically a nitrogen-dominated atmosphere similar to Earth's, based on subtle signals in the thermal emission of the planet. These results are preliminary, suggestive, not confirmed. More observations are being planned and conducted, but if they're right, LHS 1140b has a substantial atmosphere made largely of nitrogen in the habitable zone of a quiet star 41 light years away. The question of whether that atmosphere also contains water vapor, carbon dioxide, in amounts consistent with a greenhouse effect that could warm the planet enough for liquid water, is what the next set of observations will try to determine. We may know within the next few years whether LHS 1140b has an atmosphere that could support liquid water and potentially life, the search for biosignatures, what life would look like from space. If life exists on another planet, what would we see? How would we know? We would look for biosignature, chemical signatures in the atmosphere that are consistent with biological processes, inconsistent with purely geological or chemical explanations. The most discussed potential biosignature is oxygen or DOIS, the molecular oxygen that makes up about 21% of Earth's atmosphere. Oxygen is reactive. It combines readily with minerals, with other gases, with organic compounds. If you leave oxygen in a planetary atmosphere without a continuous source, it disappears on timescales of millions of years. On Earth, the source of the oxygen is photosynthesis. Plants, algae, cyanobacteria all produce oxygen as a byproduct of converting sunlight and carbon dioxide into sugars. Without photosynthesis, our oxygen would be gone in a few million years, locked up in minerals and oxidized organic compounds. So finding abundant oxygen in a planet's atmosphere would be a strong suggestion that something is producing it continuously. The most obvious candidate being photosynthetic life, but scientists are careful. Oxygen can also be produced abiotically, without life. Photolysis, the breakdown of water by intense ultraviolet radiation, can produce oxygen and hydrogen, the hydrogen being lighter, escaping to space. The oxygen remaining, this is called a false positive, a non-biological process that produces a biosignature to distinguish between biological and abiotic oxygen. Astronomers would look for other signals as well. The presence of ozone made from oxygen would strengthen the case. The presence of methane alongside oxygen would be particularly interesting because methane and oxygen react with each other. They shouldn't coexist in large quantities without something continuously producing both, and the most compelling biosignature would not be any single molecule, but the combination of molecules in quantities and ratios that cannot be explained by any known non-biological process. The vegetation red edge, another potential biosignature, is more subtle. On Earth, vegetation has a characteristic spectral signature. It absorbs red light for photosynthesis, but strongly reflects near-infrared light because the internal structure of leaves scatters near-infrared very efficiently. This creates a sharp, distinctive step in the spectrum at the boundary between red and near-infrared, called the vegetation red edge. If a planet is covered in photosynthetic vegetation, this spectral signature might be detectable from light years away in the reflected light spectrum of the planet. It wouldn't prove that the vegetation is exactly like Earth vegetation. Different photosynthetic pigment could produce different spectral features, but any life that uses photosynthesis likely has some form of spectral contrast between what it absorbs for energy and what it reflects, signature written in color in the reflected light of an entire planet, Phosphin on Venus. In 2020, a team of astronomers announced a detection of Phosphin VABA in the atmosphere of Venus. Phosphin on Earth is produced mainly by biological processes, bacteria in oxygen-poor environments, and by human industry on Venus. There is no known geological or chemical process that would produce the amount of phosphin claimed to be detected. The announcement caused enormous excitement because Venus, at certain altitude in its atmosphere, has temperatures and pressures that are within the range that some microbial life could theoretically tolerate. However, the claim was immediately disputed by other scientists who questioned the analysis, and the data reduction subsequent analyses found significantly less phosphin than originally claimed, perhaps none at all. The Venus phosphin story is a good example of how science actually works. An extraordinary claim requires extraordinary evidence. The claim was made. It was scrutinized. It became less certain. Further observations are ongoing. The answer is not yet settled what the true biosignature detection would look like. If we ever confidently detect a genuine biosignature on an exoplanet, it will not be a single observation, a single molecule, a single telescope. It will be a convergence of evidence, multiple molecules at multiple wavelengths, confirmed by multiple telescopes, multiple teams checking each other's work over years, perhaps decades of observations. It will be the most careful, most scrutinized, most verified scientific result in history, because the implications are so profound that the evidence must be absolutely irrefutable before any responsible scientist makes the claim. We are not there yet, but we are getting closer with every observation, every improved instrument, every passing year of astronomical data. The Fermi paradox: if there's life out there, where is it? In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos, discussing the possibility of extraterrestrial intelligence. And Fermi asked a simple, devastating question: where is everybody? The logic behind the question: the Milky Way galaxy is approximately 13.5 billion years old. It contains 200 to 400 billion stars, many of them much older than our Sunday. If intelligent life can arise around a star, as it apparently did around ours, and if that life can develop technology as we have, then, given the age of the galaxy, even a civilization that develops star travel at a tiny fraction of the speed of light could have colonized the entire Milky Way in only a few tens of millions of years, which is a long time by human standards, but a tiny fraction of the galaxy's 13.5 billion year age. Even without star travel, a civilization with radio technology broadcasts signals that travel at the speed of light. We have been doing this for about 100 years. Our radiosphere, our bubble of accidental radio transmission, is 100 light years in radius. A civilization 1 billion years old would have a radiosphere 1 billion light years in radius, covering a significant fraction of the observable universe. And yet, we have detected no such signals, no signals of any kind, from intelligent extraterrestrial civilizations, despite decades of searching with increasingly sensitive instruments. This is the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial intelligence in the universe and the complete absence of any evidence for it. Proposed resolutions, many explanations have been proposed for the Fermi paradox, none of them fully satisfying, because if any were clearly right, it wouldn't be a paradox anymore. The great filter, one of the most discussed and sobering explanations, is the great filter. The idea that somewhere in the chain from simple chemistry to star-faring civilization, there is a step that almost nothing gets through our filter that eliminates the vast majority of potential civilizations before they can spread across the galaxy. The question is where that filter is. If the great filter is behind us, if it was something that we already passed through the origin of life, perhaps, or the development of complex cells, or the evolution of intelligence, that would be relatively comforting, because it means we got lucky, we're through the filter, and we might have the galaxy largely to ourselves. If the great filter is ahead of us, if every civilization reaches our stage and then destroys itself or runs into some other catastrophic obstacle before reaching the stars, that would be very bad news for us, because we'd be approaching that filter, whatever it is. If we find simple life on another planet in our solar system, on Mars, on Europa, in the clouds of Venus, that would actually be bad news in a specific way, because it would imply that life is not the filter. Life arose independently, twice, right here, in our backyard. So life must be common, and the filter must be something else, something ahead, the Zoe hypothesis. Another proposed solution is that intelligent civilizations are out there, but they are deliberately not communicating with us, leaving us undisturbed, the way a nature reserve preserves wildlife without interfering the rare Earth hypothesis, perhaps complex multicellular life, is extraordinarily rare, requiring a very specific set of conditions that are rarely all present at the same time. Perhaps Earth, with its large moon, stabilizing its axial tilt, its Jupiter, deflecting incoming comets, its position in the galactic habitable zone, its plate tectonics, its liquid water, ocean, its oxygen atmosphere is extraordinarily unusual and complex life, as rare as the conditions require the great silence. Perhaps the universe is simply very large and very old, and intelligent life, while not unimaginably rare, is still sparse enough that our radiosphere has not yet reached any other civilization, and their signals have not yet reached us. Perhaps we need only to wait. The honest answer is that we don't know. The Fermi paradox remains genuinely unresolved. We have no confirmed evidence of extraterrestrial intelligence. We do not know whether this means there is none, or whether we simply haven't found it. The search continues. The wow signal, the one time we thought we heard something on August 15, a radio telescope at the Big Ear Observatory at Ohio State University, was scanning the sky as part of a SETI search, the search for extraterrestrial intelligence. The telescope detected a strong, narrowband radio signal at a frequency of 1420 MHz, close to the frequency of hydrogen emission, a frequency that some scientists had long suggested would be a logical choice for an extraterrestrial civilization trying to communicate, because it is a universally known astronomical landmark. The signal was so remarkable that the astronomer reviewing the printout, Jerry Eman, circled it in red pen and wrote one word in the margin: wow. The wow signal has never been detected again, despite many attempts with many telescopes, including the original Big Ear telescope, before it was demolished in 1997. It remains the most compelling candidate signal for an artificial extraterrestrial origin ever detected. In the history of SETI, it also remains unexplained whether it was a narrow band signal from a natural astronomical source, that we haven't identified a brief, unmissed artificial broadcast from somewhere out there, or something else entirely. We don't know. One transmission detected once in 1977, not seen again in 47 years of searching the universe, keeping its secrets as it always has, but letting one strange, unexplained whisper through just once. Europa and the search for life in our solar system close to home, while we search the distant exoplanets for signs of life. There are places much closer that may harbor it. Europa, one of Jupiter's 4 large moons, is about 628 million kilometers from Earth at its closest. Under its cracked Itze surface is an ocean of liquid water, kept liquid by tidal heating as Europa flexes under the enormous gravitational force of Jupiter. Europa's ocean is about 100 kilometers deep beneath an ice shell that is perhaps 10 to 30 kilometers thick. The total volume of liquid water in Europa's ocean is about twice the total volume of all of Earth's oceans combined. And at the bottom of Europa's ocean, where the liquid water meets the rocky silicate seafloor, there are almost certainly hydrothermal vents fueled by the tidal heating that keeps the ocean liquid. On Earth, hydrothermal vents on the ocean floor support rich, diverse ecosystems that don't depend on sunlight at all. Chemosynthetic life that uses the chemical energy of the vent fluids as its energy source. Could the same thing be happening in Europa's ocean? Could there be life in that cold, dark, distant liquid water ocean around Jupiter? We don't know. We haven't been there yet. The NASA Europa Clipper mission, launched in October 2024, is on its way to the Jupiter system, where it will conduct close flybys of Europa, studying its surface, its magnetic field, its composition, and searching for signs of material from the subsurface ocean brought to the surface through the cracks in the ice. It will not land on Europa. It will not drill through the ice. That is beyond current technology, but it will tell us much more about whether Europa has the conditions for life than we know now. And Enceladus, Europa, is not alone. Saturn's moon, Enceladus, is another world with a liquid water ocean under ice, and unlike Europa, Enceladus has been observed to be actively venting material from its ocean into space through geysers. At its south pole, the Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through these geysers and detected water vapor, ice crystals, and organic molecules, including complex organic compounds, and critically, molecular hydrogen. Molecular hydrogen in contact with water is a sign of hydrothermal activity on the seafloor, of reactions between hot rock and water that produce hydrogen as a byproduct on Earth. These reactions near hydrothermal vents are used as energy by certain microbes, organisms that consume hydrogen and carbon dioxide and produce methane in the process. Enceladus has water, organic molecules, hydrothermal activity, and a chemical energy source that life on Earth is known to use. The case for the habitability of Enceladus ocean is among the strongest of any world in the solar system, other than Earth, a future mission that could sample the geyser plumes of Enceladus more comprehensively, looking for specific signs of life, amino acids, shell membranes, chemical isotopic ratios that only biology produces, could answer the question of whether life exists in our own solar system beyond Earth, what the strange worlds tell us about ourselves, the context of everything. We have visited many worlds. Tonight, iron rain, lava oceans, rock rain, puffed up gas giants, diamond interiors, retrograde orbits, rogue planets. In the dark, the oldest planet in the universe, Earth-sized worlds, inhabitable zones, 7 planets around one tiny star, the nearest world we know about only 4.2 light years away. And the silence, the profound silence of a galaxy, we cannot yet tell whether is empty of others or full of them, simply not talking to us. All of these worlds tell us something about our own. They tell us that our world is not what any uninformed observer would have predicted as a typical outcome of planet formation. Earth is stable, calm, temperate, blessed with liquid water, a large moon that stabilizes its axial tilt, a thick enough atmosphere for greenhouse warming, but not so thick as to trap all heat, a magnetic field deflecting solar wind, active plate tectonics, recycling carbon, keeping the greenhouse in balance over billions of years. The universe has produced worlds where it rains iron, worlds covered in lava oceans, worlds with rock atmospheres, worlds almost perfectly black, worlds with rock rain and diamond interiors, and retrograde orbits around 2 suns. It has also produced this, the blue planet, the water world, the place with seasons and weather and a sky that changes color from deep blue at noon to orange and pink at sunset. The universe did not have to make Earth this way. The universe has made worlds every other way imaginable, and many that were unimaginable until we found them, that it also made this particular balance, this particular stability, this particular combination of condition that allowed 4 billion years of unbroken life. And eventually, you lying somewhere thinking about iron rain 640 light years away is not something to take for granted. The philosophy of strange worlds, what the extremes teach, there is a specific kind of understanding that comes from encountering the extremes when you know only one example of something you don't know what is essential about that example and what is accidental, what is required, and what is merely the particular way. This particular instance happened to turn out before exoplanets were held one planetary system. And we didn't know which of its features were necessary for planets to form and which were coincidental, specific to our history. We didn't know where the gas giants always formed in the outer system, where the rocky planets were always in the inner system, where the systems always had orderly, nearly circular orbits. Now we know the answer to all of those. Question is no, none of those things are necessary. They all vary enormously across different systems, and that teaches us not just about other planets, but about our own. Why is Jupiter where it is? We think we know now. Early giant planet, migration. In our early solar system, Jupiter and Saturn may have migrated inward and then outward in a complex gravitational dance that shaped the architecture of our inner solar system and may have been crucial for the eventual emergence of Earth as a habitable world. We know this because we've seen what happens when gas giants migrate inward without stopping. Hot Jupiter's systems cleared of smaller inner planets. Our Jupiter stopped at the right place, just far enough out to protect the inner system, rather than destroy it. One more lucky circumstance in a long list of lucky circumstances that made Earth what it is. The view from other worlds, imagining alien nights. Let me take a few minutes to do something different, something more imaginative. Let's imagine what the night sky would look like from some of the worlds we visited from TRAPPIST 1E, standing on the surface of TRAPPIST 1E. If it has a solid surface and an atmosphere, you would look up at a sky where the star appears larger than our Sunday from Earth, rather dimmer, a dark orange-red disk, almost never below the horizon. If you're on the permanent day side and you could look up and say other worlds, the other TRAPPIST 1 planets are so close to each other in orbital distance that they would appear in the sky not as points of light, but as discs visible to the naked eye, TRAPPIST 1F. The next planet outward would appear as large as or larger than the full moon appears from Earth, a disk in the sky with visible features. If it has clouds, you'd see the patterns from the surface of TRAPPIST 1E, and the other planets closer in would also be visible as discs moving relatively quickly across the sky as they orbit in their few-day periods. It would be a sky full of worlds, full of other planetary disks moving against the backdrop of the stars, a view that no planet in our solar system has, because our planets are spread over enormous distances from each other, from the rogue planet. On a rogue planet drifting through the galaxy, the night sky would be the most profound of all. No sun, no nearby star at all, just the galaxy, the Milky Way, or whatever galaxy the rogue planet is in stretching across the sky in a band of hundreds of billions of stars, and the darkness would be more complete than any darkness on Earth, because even on Earth, even in the darkest desert far from any city, you are illuminated by the light of the moon and the stars and the reflected light of the galaxy. On a rogue planet far from any star, the surface would be dark, lit only by the collective light of billions of distant stars and the glow of the Milky Way itself, ASCII, so filled with stars that there are no dark patches between them, just a continuous carpet of light across the whole sky, from a world that has no sun but is never truly in darkness, from a world with two suns, on Kepler on Altıp, or on one of its moons, the sky would have two sources of light moving independently over the course of weeks. Some days they would be close together, a double sun rising side by side, almost touching in the sky, their combined light, warm and bright. Some days they would be separated by a significant distance in the sky, a larger, more orange sun and a smaller, redder one, setting at different times, rising at different times, creating complex patterns of shadow, two shadows for every object in different, subtly different colors, a world of double shadows and double sunrises. The universe has made all of these plus, and they exist right now while you lie here listening, and the night sky above each one is real, and the physics is the same everywhere, the same laws, producing radically different experiences of what a night sky is. The closing, we are made of star stuff, and so are they. We have come a long way tonight from the iron rain of WASP 76b to the lava oceans of K2141b, to the puffy balsa wood density of Tresquatrip, to the fragile hope of Kepler U6 and LHS 1140b, to the seven worlds of TRAPPIST-1, to the nearest known planet Proxima Centauri b, 4.2 light years away, to the silence of the Fermi paradox and the one unexplained whisper of the wow signal in 1977, to the ice-covered water oceans of Europa and Enceladus, possibly not empty. All of these worlds were made by the same processes that made Earth, gravity pulling together the scattered remnants of dead stars into disks around new stars, the disk cooling, the matter clumping, growing, colliding, merging until worlds emerge. The conditions on each world are determined by how far from the star it ended up, what the star is like, what elements were available in the disk, what happened to the planet in its early chaotic history, and the universe doesn't care whether the result is hospitable or hostile, beautiful or terrifying. From our perspective, it follows only physics. Iron rain, from a physics perspective, is as legitimate as spring rain on a temperate Rotsky planet. Both are just physics operating in different conditions. What makes Earth special is not that it defied physics, but that physics here, under these conditions, around this particular star, in this particular galaxy, at this particular time, happened to produce something that eventually started wondering about all the other places. Physics was producing different things. The iron rain of WASP 76b is happening right now, 640 light years away. Iron droplets falling from iron clouds on a world that has never known any other kind of weather. The lava ocean of K2 141b is churning right now 202 light years away. Rock vapor rising from a surface of molten stone, moving in the supersonic winds to the dark side and falling as rock rain in the eternal night. The silence of the deep Europa Ocean is being broken right now, somewhere by the flow of water around a hydrothermal vent on the seafloor, 628 million kilometers away around Jupiter in our own solar system. And you are here on this planet made of atoms from the same exploded stars as was Tujublonambi and Ktu et Huntel or Innerfürb and Kepler-6 and Europa and every other world in the universe. The iron in your blood was forged in a star that ended in a supernova. The iron raining on WASP 76b was forged in a different star that ended in a different supernova, but the same process, the same physics, the same universe. You are made of star stuff, and so are they. All of them, every iron drop, every lava ocean, every diamond interior, every rogue planet drifting in the dark, every quiet ocean on ice around Jupiter, made of the same stuff, following the same rules, just under different conditions. A last thought before you sleep, as you drift tonight towards sleep. You are on one planet among many, around one star among many, in one galaxy among many, and the universe has been making planets for nearly 14 billion years with staggering creativity and total indifference to our expectations. Most of those worlds are nothing like this one. Most of them are too hot or too cold or too close or too far or tidally locked or too irradiated hors gazon without surfaces or rogue planets without suns. But the universe is very large and has had very long, and some fraction of all those worlds might be like this one, might have liquid water, might have stable conditions over billions of years, might have started something we don't know yet. Whether they have, we're getting closer to being able to know. And while we look and while we wait for the evidence to become clear, there is something humbling and something quietly wonderful about lying here on this planet, under this sky, knowing about all the others, knowing that 640 light years away, iron is raining from iron clouds, knowing that 202 light years away, rock is falling from a rock sky, knowing that 41 light years away, 7 rocky worlds orbit a tiny Riyadh star, and we don't know yet what's on them or in them, or whether anything is alive anywhere beyond this small, blue, lucky world. But knowing that we're looking and that the looking is getting better every year, and that the answer to the deepest question we can ask, are we alone, might come in our lifetimes. That's worth something, that's worth lying still for a moment and holding with whatever part of your mind is still awake before finally, gently, you let it go and sleep. The universe will keep making strange worlds while you rest. It has been doing this for 13.8 billion years, and it shows no sign of stopping. Rest now. The iron rain is still falling 640 light years away. The lava oceans are still churning. The rogue planets are still drifting. The TRAPPIST worlds are still orbiting. They're quiet. The Riyadh star, and somewhere, maybe something is looking up at its sky, whatever its sky looks like, and wondering the same things you wonder under yours. Sleep well. The universe is very large and very old and still not done.